you very much for your kind introduction. It's a great pleasure to be here today on this beautiful campus. And I always enjoy talking about the subject because the universe is so mysterious and awesome. Now, we've learned an awful lot in the last 100 years about the universe, both the large aspects and the small aspects. I will try to convey some of this to you in about 40 minutes. Of course, it's a very short time to talk about the entire universe. But, probably some of the details may not be understandable to everybody, but unfortunately there isn't enough time to explain all the details. But what I do hope is that I can convey the basic concepts and the ideas and the sort of the general structure of the universe as we know it today. Now, I will start talking about the large aspects. And how do we learn about the large aspects? First of all, we do experiments. Actually, in astrophysics, it's observation, and we develop models which are classified as part of cosmology. And of course, we use the cosmic rays. Here, we study the cosmic rays. We have space telescopes. This is a Hubble Space Telescope. It's about the size of a bus. We have radio telescopes. We have special satellites which carry types of instrumentation which measure particular features of the universe. And then, of course, we have ground-based observatories, astronomical observatories. Here's the Los Alamos Observatory, which you probably have seen. And so these things are used to get information about the large aspects of the universe. And what is cosmology? It asks the following questions. How did the universe come into being? Why does it look like it does now? And what is the future? Now, it uses astronomical observations. Its theoretical base is general relativity. It uses input from both particle and nuclear physics to study the early development of the universe. And what have we learned? Well, the simplest things are the following. We live on the third planet of a medium-sized star in the Milky Way galaxy. Now, there are about 100 billion stars in our galaxy. However, there are 100 billion galaxies in the observable universe. So when you actually put them all together, we have 10 to 22 stars, 10 to 22, an enormous number of stars in the observable universe. But the interesting aspect of this is that all these stars, all these visible stars, comprise less than 1% of all the matter in the universe. Just less than 1%. And that's an interesting issue. And of course, when you really think about it, despite all the developments in past history about the centrality of the Earth is just the most minute, infinitesimal thing in the entire observable universe. Now here's a picture taken with the Hubble telescope. This is called a deep space probe. Now every one of these points of light, or areas of light, is a galaxy comprising of about 100 billion stars. And these just fill the universe. And here is a typical galaxy. It's a spiral galaxy. And you can see its structure. They're generally about the order of 600,000 light years to 1 million light years across. 100 billion stars. Very often there is a black hole in the center. And from these observations, we've learned the following. That the universe has been expanding since its very beginning, 13.7 billion years ago. It's a pretty precise number based upon calculations. But however, the edge of the observable universe is about 46 billion light years away. Now, a light year, of course, is the distance traveled by light in 1 year, which is an enormous distance. And the universe is expanding because space is expanding. Space is expanding. And we can actually chart this out. We have the so-called Hubble law, which the velocity of expansion it gets larger and larger as you get further and further away from us. And the further our galaxy is away from us, the faster it is receding away from us. So that's another feature. Now, accelerators, particle accelerators, are very interesting in the following matter. We can actually create the conditions of the very early universe. For example, Fermilab, which was the highest energy accelerator before the LHC, looked at the conditions of the universe about 4 trillionths of a second after the Big Bang. Now, let me trace what we think the model is for the development. There was an enormous explosion at some point about 13.7 billion years ago. The universe was enormously hot at that point. It was very tiny. It was expanding. In about 10 to the minus 32 to 34 seconds, the various fundamental particles were created by the energy and, for example, quarks and electrons and things like that were floating around in a kind of a soup of energy, of plasma. And these quarks form nucleons, namely protons and neutrons, in 10 to the minus 10 seconds after the Big Bang. These are enormously short times. In 3 minutes, and you see what's happening is the universe is expanding very rapidly. And as it expands very rapidly, it's cooling down. And you see, as it cools down, you have things like freezing out. It's like if you have a mixture of gases and you cool them down, various gases will actually condense into material at different temperatures. Same thing happened at the early universe. So the quarks, in 10 to the minus 10 seconds, the universe was cool enough for the quarks to form protons and neutrons. And then, actually, after 3 minutes, it got cool enough so that nuclei could form. And you see, the reason you have to wait until it gets cool, because if it's too hot, these things bounce against one another, and they break one another up. But once the binding energy is sufficiently great and the temperature is sufficiently low, you can't break them up anymore. So they freeze out. And then it took 380,000 years for atoms to form. And then, roughly about 1 billion years, stars were forming and galaxies were forming. And now here we are, 13.7 billion years from the Big Bang. And that's the model we have of the Big Bang. And that's based upon various observations and calculations. And much of this information came from measurements of the so-called cosmic microwave background. You see, when the universe was very early, there was a lot of radiation produced. And as the universe expanded, its radiation cooled down.
Sorry, Jerry, could you make that?
I'm sorry, cooled down. And finally, we got to the microwave state, and it's been measured, and it's a perfectly, the temperature of it, black body radiation, is 2.7 degrees Kelvin. 2.7 degrees about absolute zero. So the universe today is very, very cold, although it started out extremely hot, enormously hot. And these have been measured. The fluctuations tell us very much about the composition and age of the universe. And what do we know about the composition? Well, it's very interesting because if you look at, we can say that matter and energy are equivalent. Everybody here has probably heard about the most famous equation in physics, and that is E equals mc squared. So I can make energy and matter absolutely equivalent and talk about the energy and the matter of the universe as being stuff. And I can ask the question, what does this stuff consist of? Well, it turns out that there's something there in the universe we don't understand at all. 73% of the stuff in the universe is so-called dark energy. It was discovered only about 20 years ago. Maybe 15 years ago. But it was by various observations of stars it was discovered, and we have no idea of what this energy is. But it has one very important aspect. It's anti-gravitational. It's causing the universe not only to expand, but expand faster and faster. This dark energy is pushing the universe to accelerate its expansion. And this is a very mysterious thing, and there's a lot of research going on to try to understand what this dark energy is. The other component of our universe is the so-called cold dark matter. We don't know what that is at all either. What we do know is that it doesn't consist of atoms, what we are made of, what this room is made of. It consists of some kind of exotic particle that we know nothing about. So the only part of the universe, we only know about 4% of the contents. We only understand 4% of the contents of the universe, and that's the atomic matter of the universe. And so you see, for you young students here, there's a lot to be learned, and I hope that some of you will participate in the great exploration to understand what makes up the major part of our universe. But only 4% is understood at all at the present time, which is actually an incredible thing. But so here's the current models of the expansion of the universe. The red curve is based upon what is now thought to be the correct expansion of the universe. And you can see it was down to roughly 0 at 13.7 billion years ago. There is not, you can see the now right here. And about 25 billion years from now, the universe will be about 4 times larger, and you can see that the rate of expansion is accelerating. So there's an awful lot to understand about the universe and its large structure. So what do we know about the contents of the universe? Dark energy, as I said, virtually nothing. Dark matter, we know virtually nothing. It's being searched for in various laboratories. People are trying to create it at accelerators. And so those are the two components, which are the largest components we know nothing about. On the other hand, if we consider atomic matter, the research of the 20th century has uncovered the structure of the atom and the structure of its constituents. And this is what I tell you a little bit about right now. So this is the 4%. So what do we use? What kind of tools do we use to investigate the subatomic world? We use particle accelerators, and I'll tell you why. We have particle detectors. We have scattering experiments. We bounce one particle off another particle, and this allows us to probe the particle structure and the forces that act between the particles. It also allows us to produce new types of particles that existed in your universe. Why is it here? You want to sit here because I'm blocking your way. Okay. So here is the first experiment. This is the pioneering experiment which uncovered the structure of the atom. It was done by Ernest Rutherford in the early part of the 1900s. It was published in 1911. And it was a very simple experiment. You had a radioactive source in radium. It emitted alpha particles, which were just the nuclei of the helium atom. They came out at a reasonably low energy, but they could bounce off a metal foil, and with gold was used. It hit a zinc sulfide screen, and actually, the way it was observed is to have students count the little pulse of light looking through a microscope. You can see how primitive it was. But this experiment, as primitive as it was, discovered the atomic nucleus. Now, there were two models at that point. One was a so-called Tom Pulley model of J.J. Thomson. And the idea, you see, a nucleus has to have a positive particle of some sort. An atom is electrically neutral. There's a positive charge and there are electrons. And so the question is, how is the positive charge distributed? Well, J.J. Thomson, who was a very famous British physicist, he discovered the electron. thought it was like a plum pudding. The positive charge was spread over a big regional area, the size of the atom, and the electrons were in it, like plums in a pudding. And that was considered to be a reasonable model. A Japanese physicist thought it was more like the solar system, that the nucleus was in the center, and the electrons went around it. And so these were two competing models. And here's a picture of Rutherford on the right, and Hans Geiger on the left. And this is at their laboratory in Manchester University. And the thing which is interesting, you see this little table here. That was the size of the experiment. What I want you to remember is when we talk about the experiments of the present, looking at subatomic structure. So now the point is to go back. Let me just show you why the plum pudding didn't work. You see, in a plum pudding model, the idea was that the alpha particle was much, much heavier than the electron. And the electron, if you consider the ratio, the alpha particle was like a 8,000 kilogram truck hitting a 1 kilogram stone. What do you expect happens? The truck goes through, nothing happens. Now, if you have the truck hit something which is 50 times heavier, then it's going to bounce back. And that's what, if that 50 pounds, if that central collision occurred with something quite small, it would hit it and bounce back. And that's what was observed. And that's why the so-called solar system model was confirmed in Rutherford's famous experiment. Now, of course, what happened was the proton was discovered in 1990. Rutherford made the observation that the proton must be the nucleus of the hydrogen atom. Chadwick discovered the neutron in 1932, and therefore we had the constituents of the nucleus. But then the question came up, are they fundamental particles? Are they made up of other things, or are they just single entities unified in their structure? And those are the questions. So I want to now talk to you about electron microscope to give you an idea of why physicists want to scatter particles against other particles. You see, if you want to see something with light, and you want to resolve it, the wavelength of the light must be much smaller than the size of the object. Otherwise, you cannot resolve it. And you see, now the point is, to take an electron, quantum mechanics says something very strange about it. It says this electron has both a particle nature, and a wave nature. So the electron has a wavelength. You can use the wavelength of the electron. But not only does it have a wavelength, but you can make the wavelength smaller and smaller by increasing its momentum. So the idea, if you can accelerate the electron to be very fast, you can see enormously smaller things. And that's why an electron microscope can be used to look at viruses when an optical microscope doesn't work. But the interesting thing is that all particles have wavelengths. So I can accelerate all kinds of particles and use them as accelerators and measure exceedingly small things. So for example, if you look at the nucleus with a low energy, it looks like sort of a sphere with no structure. If you go to higher energies, you can start seeing the structure. And of course, again, the wavelength is equal to h, which is Planck's constant, over the momentum. And of course, the momentum of the particle increases with its energy. So the higher the energy, the smaller the object you can probe with it. And that's a very fundamental rule in particle physics and in all diffraction phenomena. So now we've been able to discern a hierarchy of matter. If you look at a chair, at us, let's consider we're looking at it with magnification 1. If we want to look at the atom and see an atom, we have to increase the magnification by 100 million, which means very high energy. If we want to look at the details of the nucleus, we have to increase the magnification another 100,000 times. And now, we said the nucleus is made up of neutrons and protons. If we want to look inside the neutron and proton and see what's there, we are now examining it with another magnification of 10,000. So you can see what kinds of increases in energy you need in order to get smaller and smaller observations. So now I want to tell you about how we discovered quarks and how quarks were developed as a theoretical model. First of all, there was new technology after World War II, and there were new accelerators, which are new detectors, and a large number of particles were discovered, an enormous number of particles. We're talking about hundreds of particles. What do you do with hundreds of particles? How do you deal with them? Well, two very bright, brilliant physicists came up, namely Murray Gell-Mann and Yuval Ne'eman in 1961, said they developed a mathematical model called the Eightfold Way, which was able to classify particles according to their spin. Now, particles have spin. It's like they have the properties of a rotating top. We basically have the quantum mechanical description of it, but they have a certain spin. We don't think they're actually rotating, but they have the properties of spin. So it turned out that this classification became like the periodic table of the elements. This is the periodic table of the particles. And what was important about the periodic table of the elements? What was important was the following. It not only told you that it had a place for all the particles that existed, but it also predicted the existence of particles that you haven't yet discovered. And that was the strength, that was the strength of the periodic table of the elements, because that was done with elements. This was done with particles. And here are the families. This is the so-called particle periodic table. And you see every dot, don't worry about the structure or the mathematics, it's not important. But every dot there corresponded to a particle, some of which were predicted, some of which were discovered. The point was that every one of these particles was discovered. And that was awesome. Because it was just a mathematical model with essentially no dynamics in it. Why does this model work? And that was the big question. And this was the origin of the quark model. So the quark model was proposed by Gell-Mann again and George Zweig independently. And the quarks were proposed as the building blocks of these strongly interacting particles. And they generated the structures and the symmetries of the family. And I'll show you that. So what were the quarks? There were three types at that point. There was the so-called up quark, down quark, and strange quark. They all had spin 1/2, but they had a peculiar characteristic, and that's one of the reasons that the quark model was thought to be absolutely wrong when it was proposed. These quarks have fractional charges, and no particle in nature had ever been observed with fractional charges. But you see, the up quark was if you said that the proton is charged 1, the electron is charged -1. The up quark was charged 2/3. The down quark was charged -1/3, and the strange quark is -1/3. And here's the way they were put together. For example, the proton would be 2 up quarks and a down quark. And if you do the calculation, you see, well, 2/3 plus 2/3 is 4/3, -1/3 is 1. If you look at the neutron, it's 2 down quarks and an up quark. minus 1/3 plus minus 1/3 again is minus 2/3 plus 2/3 is 0. These are the charges of the proton and neutron. And that's the way it worked. It was as simple as that. And so that was some sort of plausible argument. And for example, let me show you how it generated families. That families were really, you don't need any higher mathematics to even see how it generated the structures of families. For example, here's the family of spin equal 3 halves. Notice the top one, very top of the triangle, 3 strange quarks. The next row, 2 strange quarks. The next row, 1 strange quark. The next row, no strange quarks. Go to the right hand point of the triangle. 3 up quarks. Next row, 2 up quarks. 1 up quark, no up quarks. And the same thing for the other side with terms of down quarks. You can see how these things generated that structure. And it was beautiful. But the question is it true? The real question is, what do you do to find out whether it's true? Well, the thing you do is you search for it. You search for quarks. And so that began. Are quarks real? There were many unsuccessful searches. They were searched for in accelerators, in the cosmic rays, in the terrestrial environment, seawater, meteorites. Not a quark is found anywhere. And and of course people said, it's obvious. This is a crazy idea. Who ever heard of particles with fractional charges? So the general point of view in 1966 was that quarks most likely are just mathematical representations, useful but not real. And the particles we know of have diffuse structures and no constituents, and no building blocks. And what did some of the great physicists of the time say? Well, Murray Gell-Mann, who was the father of the quark model, said the idea that mesons and baryons are made primarily of quarks is hard to believe. Another physicist who's working on it at these issues said additional data are necessary and very welcome to destroy the picture of elementary constituents, namely quarks. Another physicist, Kurt Gottfried, said, I think Professor Bjorkane and I constructed the sum rules in the hope of destroying the quark model because it was so bizarre. And then, of course, in 1969, a physicist by the name of J.J. Kokeny wrote a monograph. He was a physicist at CERN. And he said, of course, the whole quark idea is ill-founded. So it was a theory that was in great disrepute. And so what happened? Well, but you might have said, well, what did people think the quark model, the proton and neutron consisted of in those days? I mean, what was the model? The model was equally bizarre. It was called nuclear democracy, or the bootstrap model. And the point was that particles were just composites of one another. For example, the proton is equal to a pi meson plus a neutron plus other particles. A neutron is a pi minus plus a proton plus other particles. It's as if we said that all the individuals in this audience are composites of one another. Now, that's a crazy idea, but in quantum mechanics you can make such statements. So in this model, the particles had diffuse substructures and no building blocks. Now, quarks were discovered between 1968 and 1972 by MIT SLAC collaboration. Now, SLAC stands for Stanford Linear Accelerator Center. It's located at Stanford University. I'll talk a little about it. The experiments utilized the equivalent of a very powerful electron microscope to examine the insides of the proton and neutron. The linear accelerator at SLAC provided 20 billion electron-volt electrons, so you get very, very tiny short wavelengths. The effective magnification was about 60 billion times greater than with ordinary light. And so here is a picture of the Stanford Linear Accelerator Center. This is the beginning of it. It's 2 miles long. It was so long it had to be built over a major highway. The actual accelerator is underground. The experiments were done in this hall. Here are the spectrometers used. I won't go into great detail, but these were the biggest things in physics at the time. And the idea was there was a target at this right at the apex of it, and electrons came in, scattered from the target. The scattered electrons went up this. This is a bunker in which the particle detectors were held, and there were magnets to essentially pick out particular energies, and that was it. This one was 75 feet long. This one was 150 feet long, roughly 50 meters, 25 meters. This one weighed 3,000 tons. And the whole idea was the same thing as the Rutherford experiment, except different. You see, this was the current model. The top one was the model of the proton. And of course, if you had an electron going through here, it would be like going through charged jello. It would not do very much. It wouldn't scatter very much. It's like having a charged gelatin of some sort. If you had constituents here, and of course it turns out that the constituents inside the proton and neutron were roughly 10 times heavier than the electron, so the electron could actually scatter off these constituents. And large angle scattering implies smaller particles inside. And of course, the measurement showed, here is the probability of scattering and the vertical axis. Down here is something called momentum transfer. The angles get larger as you go to the right. The scattering was more or less constant. This is what you expect in terms of the old models, and there was such a difference, it was clear that the old models did not work. And so basically large angle scattering observed, indicating small constituents inside the proton and neutron. The image reconstruction indicated these were point-like, which meant they were so tiny we could not measure the upper limit of the size of them. We could only get an upper limit on their size. They're probably much smaller than what we observed. And there were neutrino experiments done at CERN, which, along with the electron experiment, showed that fractional charges were consistent with the quark model, and all the older models of particle structure were abandoned between 1972 and 1980, and quarks had to be there. As strange and as bizarre as this model was, it was the correct model. Now, you might ask the question, have any quarks ever been seen in nature? That was one of the reasons you didn't believe in them in the first place. The answer is no. So you say, well, why should you believe in them now? Well, it turns out that when you make a discovery which is really kind of bizarre, it always indicates new kinds of physics. And new kinds of physics was developed. And so there was something called quantum chromodynamics, which was developed by Wilczek, Gross, and Pulitzer. And it indicated that the force between quarks was quite different from all other forces that had been studied in the past. You know, if I take an electron and positron and I move them apart, the force decreases as the square of the distance. You probably all remember that. It's true with the gravitation force. This force is really strange because if I pull two quarks apart, the force is basically constant. It increases slightly. It's constant. And the force between them, between two of these tiny quarks, is 15 tons of weight, equivalent of 15 tons of weight. Can you imagine these two little tiny things having the equivalent of 15 tons of weight? That's how strong this is. This is called the strong force. If I try to separate a quark and an antiquark by 1 centimeter, I need an energy to do that of 10 to the 13th billion electron volts. If I try to build an accelerator to produce such an energy, that accelerator would be basically the size of our solar system, the outer planets of our solar system. So you can see, we cannot produce, as far as we know, we cannot produce enough energy even to think about separating these things and getting a free quark. A free quark, and in principle, probably can never get a free quark. Because what happens is that as you start pulling the quark and anti-quark apart, that force field, which is roughly constant, actually snaps. And when it snaps, you get a quark and an anti-quark at the two other ends. You see? Like this. So one here and here. This is how you have particle production in this model. And all kinds of experiments have been done which have verified this behavior. So the quark model and quantum chromodynamics are new aspects of physics that are certainly part of our standard model today. So the question is, now we ask the question, how solid is matter? Now, if you look at how big, what is the upper limit in the size of quarks today? Well, they are smaller than 10 to the minus 17 centimeters. 10 to the minus 17 centimeters. So the question is, and of course the electrons also are smaller than 10 to the minus 17 centimeters. So if I take a carbon atom and I ask the question, how much of the volume of the carbon atom do the nuggets of matter, quarks and electrons occupy? Well, it turns out, if you do the calculation, it's of the order of 3 times 10 to the minus 25. So fundamentally, we are all empty space. The amount of our matter, atomic matter, that is occupied by the nuggets of matter is infinitesimal. So we're empty space. It's hard to tell you that. But, so you ask the question, well, why can't, if we're empty space, why can't I put my hand through this wood here? After all, there are so few nuggets in my hand compared to also in the wood here, they should just go through. The reason I can't do that is fields. The solidity of matter comes from fields. Now, what is a field? Probably the biggest experience you've had of a field is as a child, you play with little magnets. And you know that if I have a magnet, I can pull in some iron. There's something that goes across, and it's pulling in that iron. So that there's a real reality of the field. You felt it. The electric fields are the same. And so the point is, when I try to put my hand through this wood here, the fields in the wood are repelling the electrons in my hand, and vice versa. So I can't put it. So the point is, the solidity of matter comes not from the nuggets of matter, but from the fields. And fields are enormously important in our idea of what the universe consists of. What about weight? After all, I can say at a certain level, all of us are made up of 3 things. Electrons, up quarks, and down quarks. I know the approximate mass of these things, therefore I can know what the weight would be. So if I took a 150-pound individual, and I took all the quarks and all the electrons in that individual, and I put it in a weightless bottle, and I weighed it would only weigh 2 pounds. So your weight doesn't come from your nuggets of matter either. Where does it come from? It comes from 2 sources. It comes from the fact that these quarks in the nucleus are moving very, very, very fast. They have big kinetic energies, and therefore, again, I use E equals mc squared, and that energy has weight. Also, also, there are force fields holding the quarks together. And, of course, if I measure all the energy in those force fields, that also has to be. And those two effects give me 148 pounds. So, again, most of our weight comes from E equals mc squared. I bet you didn't learn this in high school. Now, there's another question. Are quarks the most fundamental thing? Are there things inside of quarks that make up the quark? Is there another layer of constituents within quarks? Well, again, there's nothing in physics that says there can't be. But if I had to bet on it, I'd bet against it. You might ask why. And the reason I would bet against it is the following. Remember I told you that the wavelength is 1 over the wavelength is basically 1 over the energy, roughly speaking. And so if I want to get if I want to get something that fits into 10 to the minus 17 centimeters by quantum mechanics, I either have to have a half a wavelength or 1 wavelength that fits inside. And that is such a tiny wavelength that when I ask what is this means that whatever is inside the quark is moving with enormously big high energies. Enormously. It means I have to have an enormously powerful force to hold these things in. And remember I told you about the strong force being 15 tons? Well, if I put the limit, the upper limit, let's say I said the quark was as large as 10 to the minus 17 centimeters, probably a lot smaller. The force holding these things in would have to be 100 million times stronger than this force of 15 tons that I told you about. That's why I would bet against it. You know, it's still possible. I could be absolutely wrong, but this would imply incredibly powerful forces in the universe that we know nothing about. So we now have 6 quarks. They have all kinds. They all have fractional charge, spin 1/2. The thing which is mysterious, they all have different masses. The heaviest quark is the top quark, and that is incredibly mysterious because this tiny thing has about the weight of a gold atom. We can't understand why it's so heavy. So that's another mystery. So we have the question, but as I said, it's an experimental question as to whether quarks are the smallest thing. And of course, if we can now go to the Large Hadron Collider, where experiments are being done to check into that. And of course, the thing about the Large Hadron Collider is it provides another factor of 10 of magnification. So let me say a few things about that. But before I do that, I want to make one point. All these experiments up until recent years, let's say 10 years ago or so, involved so-called fixed target experiments. You shoot a beam at a fixed target. Now, that was a very powerful method, but it has one limitation. Remember I told you need high energies to probe. But the effective energy for probing in a fixed target experiment doesn't go as the energy, it goes as the square root of the energy for very high energies. And that's unsatisfactory. If you really want to get to small distances, it means you've got to build enormously big accelerators. So it turns out there's a new principle now, and that is having colliding beams. And the idea there is you have 2 beams of equal energy, and you have them collide. And they both are both projectiles and targets. And you can use actually twice, the available energy goes as the sum of the beam energies, which makes it a much more effective accelerator. So it's a much better microscope. Now I want to talk a little about the Large Hadron Collider, since Spain has played a large role in developing it. This is Ernest Lawrence, who invented the cyclotron. in 1929. You can see it in his hands there. And now here is the Large Hadron Collider at CERN. It's 14 trillion electron volts total energy. Each beam, when it gets to the design energy, will be 7 trillion electron volts. So it's an enormously big thing. It's 27 kilometers in circumference. You can see in the map here, it's both in France and in Switzerland. It's already so big, it has geographic significance. Here's what it looks like underground. There are thousands of superconducting magnets operating at 1.92 degrees Kelvin, absolute. It's the coldest spot in the universe at the present time. Well, here is one of the detectors. This is the smaller of the two detectors, two large detectors, and you can see a person down here in comparison. It's about 21 meters long, 50 meters in diameter, and it weighs 12,500 pounds, enormously heavy. It's very complex, and this is what it looks like being assembled. You can see the complexity. The two large detectors are the most sophisticated scientific instruments ever developed. They are incredibly sophisticated and complicated. And I'll show you why. Here is the other one. This is the Atlas detector. This is a big one. It's not as heavy as the CMS, but its height is equivalent to a 7-story building. It's roughly 50 meters long. It weighs about 7,000 pounds. And it's again an incredibly complicated device. You can see it being assembled here. And now I want you to think back at that experiment that Rutherford had on the table. And this is what's happened in 100 years. And this is largely because of technology and what the engineers have been able to produce in developing this technology. And so the Large Hadron Collider has major challenges. Each of these detectors have roughly about 100 million readout channels. 100 million readout channels. The collisions occur every 25 nanoseconds. So you have to be able to record these things in very short times. Atlas uses the large detector. It uses 3,000 kilometers of cable in the experiment. The data volume recorded at the front end of CMS is 1 terabit per second, which is equivalent to the worldwide communication network traffic. So the amount of information coming into the front end of these detectors is absolutely enormous. And another problem is that the kinetic energy of the beam is equivalent to the energy of a 10,000 ton ship going 20 miles an hour. So you have to be very careful with that beam. If you missteer it, it destroys everything in its path. And of course, here are various weights. I want to point out that the CMS is heavier than the Eiffel Tower. And it's also heavier than one of the destroyers in the U.S. Navy, the USS John McCain. So these things are enormously big devices and heavy devices. Here is the challenge. This is a relatively simple event. It's a collision producing two jets. And 100 billion events of this complexity or more, greater complexity, occur every second at full luminosity. Every second. Now, what you want to do is save about 100 of these events, and you have to make a decision based upon the topology and the energies of some of the tracks. You can imagine what a computational challenge that is, because it has to be done in real time. You do not have enough storage capacity to store every event that you get. And the only way to do it is to reduce it by this ratio, which is enormous. So that is a great computational engineering challenge of this accelerator. And here are all the things. It has a grid of 100,000 computers. massive storage devices. I want to point out that Spain played a very large role in designing and implementing this grid. And this grid is very, very important because it allows scientists all over the world to share data and also exchange information. And I should point out that CERN invented the World Wide Web. So this is one of the great practical things that came out of this high energy physics program at CERN. So here's the grid. There are tier 1 laboratories and tier 2, and they're all connected, and they all share data. And I don't have time to really go into it in great detail, but it's an enormously complicated thing. And basically, physicists from all over the world are participating in this analysis. And so, now I want to say a few words. I'm probably running out of time. Okay. I want to say a few words about the Higgs particle. On July 4th, there was an enormously important announcement from CERN. A particle such as the Higgs, it could possibly be the Higgs particle, was discovered. And I want to tell you why the Higgs is important. You see, physicists love symmetry. The application of symmetry gives rise to many physics principles and fundamental equations. And in developing the fundamental equations of what we believe is to be the correct set of equations today, a certain symmetry was used, called local gauge symmetry, which the application of which required that all particles have zero mass. Zero mass. If all fundamental particles have zero mass, then you have a great symmetry there, and you're able to use symmetrical operations. However, there's a problem there. And what's the problem? The problem is that, of course, the particles of nature do not have zero mass. So you have to basically find a mechanism and incorporate it into your equations that produce mass in particles. And it turns out that the Higgs mechanism was the simplest mechanism used. And so let me point out what the Higgs mechanism is. The idea is that all through space, there's a field. Again, we come back to field. These zero mass particles interact with the space. There's a force between them. And the greater the force, the heavier the mass. Now, let me point out why this makes sense. If you have a particle with zero mass, it travels with the velocity of light. And that's the maximum velocity you can have. Now, if it goes through something like molasses and is slowed down, then, of course, it's not traveling at the speed of light anymore. So it has to have an effective mass. And we call it mass. And the bigger the force, the more it slows down, and the larger the mass. And this was the model. And, of course, many people thought it was, again, too simple a model. But it also predicted the existence of a new particle called the Higgs particle thesis, because the point is that every field has an associated particle. After all, the electromagnetic field has the photon. The gravitational field has the graviton. The Higgs field must have a Higgs particle. And so the only thing was that the theory did not predict the mass of Higgs particles. So one had to search. Well, the search went on at CERN in a beautiful set of experiments. And lo and behold, something which had the properties of the Higgs particle was discovered at a mass of about 126 billion electron volts. And when I say electron volt, I'm using equals mc squared. That's the way particle physicists define mass today. And you can see, and the two detectors both got the same result. And so the Higgs particle looks like it's there, and it's really quite amazing. Because it really says to us, if it's true, that as far as particles are concerned, all space is filled with a kind of molasses which slows them down, a field which retards them. And this is another field. So here we have 6 quarks. We have the so-called leptons. We have an electron and 2 heavy electrons. We have neutrinos and the Higgs field, and we have the 4 forces, 3 forces actually. Actually, we have 4 forces here because we have the Z and the W, and we have the strong force, which is over with the gluon. So, in terms of, we have something called the gluon, which is here we have these 4 particles which are associated with the standard model. The Z and the W are the particles which have to do with the fields associated with the weak interactions. But we have the photon up there, the gamma ray, and we have the so-called gluon, which is the particle associated with quantum chromodynamics. And so the Higgs basically produces masses in all the particles that seem to have mass in various ways. And the only 2 particles which do not actually obey or are affected by the Higgs field are the photon and the gluon, and of course the graviton also, because the graviton also drops with the velocity of light. But I don't have time to discuss it. And now another thing that's being searched for is something called supersymmetry. I don't want to spend too much time. The idea there is that if you try to unify gravity with quantum mechanics, you need a mirror set of particles called supersymmetric particles. And they're kind of peculiar because we classify particles into 2 different types. We have fermions, which are 1/2 spin, 1/2, 3/2, 5/2. And then we have bosons, which have spin 1, 0, 1, 2, 3. So we have integral spin and half integral spin. And there are 2 different kinds of particles. They have some different quantum mechanical properties which are very important. But if you try to unify gravity and quantum theory, every fermion has a partner which is a boson, and every boson has a partner which is a fermion, which is a very interesting symmetry. And that is being searched for. And so it's required in theories, as I said, that unify relativity and quantum mechanics, general relativity, that is. And it also does something. It basically brings all the forces. You see, the forces actually have another property, they change with energy. They can get stronger or weaker with energy. But here, in the sense, here you see that if you use supersymmetry, they seem to unify that at some energy they all come together to be the same force. And that is a point of view that many physicists have, that there's a one unified force at very high energies, which as the energies go down, they separate into different forces. So that's another reason that people like supersymmetry. One other thing is, are there extra dimensions in the universe? So that's another thing that's being looked for at the LHC. You see, if you have superstring theory, that is a theory which tries to unify gravity and quantum theory. And however, in any manifestation of such a theory, it appears that you need at least 10 dimensions. And so basically, you have 9 spatial dimensions and 1 time dimension. And that's what's required. Now you said, that's crazy. We only know 3 spatial dimensions. But in this theory, the idea is that these 6 extra spatial dimensions are roll up in very short distances of the order of 10 to the minus 32 centimeters. So there's no way that they affect anything in the so-called atomic world, because that's an incredibly short distance. So, however, there are some theories which say, well, they can be as large as, these extra dimensions can be as large as 10 to the minus 18 centimeters or greater. And if they are, the LHC will be able to find evidence of such extra dimensions. Just imagine if we found evidence of extra dimensions. It would be a phenomenal thing. So these are some of the things that are being searched for with the LHC. So here it is. So the questions are quarks and electrons the smallest building blocks of matter? That's one of the questions. Are there new particles, new fields, new laws of physics? Are there extra dimensions? Oh, one other thing is, what happened to antimatter? That's another interesting issue. I just wanted to mention that. You know, if there were absolute symmetry between matter and antimatter, we would not exist. The universe as we know it would not exist. And the reason for that is the following. When the universe in the very early stages, and you just had energy, you made particles and antiparticles. But as the universe cooled down, if they annihilated it would just be a radiation-dominated universe. And there would be no atoms, there would be no other particles. But it turns out that and the reason that we exist is that there's a very tiny asymmetry between matter and antimatter. And basically, this is why matter basically persisted and antimatter died out. And the question is, we've observed this in the laboratory, but what we have observed is only part of what's needed to have the universe exist as it exists. So that's also being searched for at the LHC. And of course, there will also be totally unexpected discoveries. The kind that always surprise people. It'll be out of left field, so to speak. Things that nobody had ever anticipated. These have happened in the past, and these have been some of the most important discoveries in physics. So I would say that the LHC is bringing a new era of discovery into the world of physics, and I hope that some of you young people here will have a chance to participate in this great adventure. Thank you.
Bueno, ¿alguna pregunta? Si es que les han quedado dudas. ¿Alguien tiene alguna cosa que le gustaría preguntar?
Sí.
Yes? Okay. Okay.
Yes. Sí,
Aquí. Pues vamos a empezar a pasar micrófono. Voy a hacer esa forma.
I need a microphone.
Necesita un micrófono.
Un micro.
I have to get a microphone.
Yes.
Oh, okay. Oh, I'll sit there. Okay.
No, no, no. Ya lo dejamos aquí.
Okay. Yes, I have a microphone here. I'm all set. So listen.
The question is coming from there.
Hello. Sí, mi pregunta es la siguiente. ¿Puede haber habido un momento, un instante infinitesimalmente pequeño en el que toda la energía, toda la masa, toda la materia estuviese en un elemento puntual y ese elemento puntual estallara? Estoy haciendo referencia al Big Bang. El Big Bang se hace multitud de partículas, crea el universo en expansión y posiblemente no sé cuál sería su idea después de un retroceso, con lo cual volveríamos a condensar toda la energía y toda la materia en ese otro punto nuevo y volvería a dar lugar a otro Big Bang. Quiere decir que posiblemente ha habido múltiples Big Bang. ¿Cuál es su opinión?
Yeah. Well, that's a very interesting question. Actually, the current theory is that there were multiple Big Bangs, and there are probably other universes out there. The problem with this whole point of view, from my perspective, is that these other universes are universes we cannot communicate with at all. There is no way that we can get any experimental information to either verify their existence or to measure any property of them. So while we can suppose that, it's getting somewhat out of the range of science. You see, science has to be really observational, and that's one of the great perplexing questions, because if you talk to most theorists today, they will say, "Oh yes, there are many universes out there. You know, possibly, you know, you're talking about incredibly large numbers." But the problem is how you can verify any such assertion. That's the problem. And I want to say, and there are two reasons that people would like to have many universes. In string theory, if you look at the possible solutions, there are possibly, you know, somebody said you had the number 10 to the 500th power solutions. Some people say infinite number of solutions. And so they say, well, every solution, and these solutions all have different fundamental constants, because there seems to be nothing to pin down the fundamental constants in string theory at the present time. And so you take that point of view, and then the point of view has been taken, well, in the inflationary model, which I didn't have a chance to discuss with you because I just didn't have time, there was a period of time when, in the very early universe, when the expansion was enormously great. And there was accelerating expansion at that point. And there was sort of frothing at the edges. And these edges broke off and bubbles broke off, and they became sources of new universes. And so the combination of this sort of bubbling or frothing plus all these solutions have led theorists to say, well, there are probably all these universes out there, each of which has different fundamental constants. The fact that we exist is only because for our universe, the fundamental constants are of such a nature that the atoms can exist. You know, if you change the fundamental constants, you get a situation where atoms can't exist because the forces are not right. And so this is called the entropic principle. And there's a big debate about that. You know, some physicists say, well, the reason you have the entropic principle is because you can't calculate properly. And others say, well, no, it seems to be more fundamental than that. So there's a big controversy in that. But the bottom line, from an experimentalist point of view, is that when you start talking about multiple universes that you cannot communicate with, you're getting more into the realm of metaphysics than physics. Because physics always should be something that allows you to get some observational information that can either verify or falsify an assertion. Is that?
¿Alguna más? Otra. He will be here near to you.
Otra pregunta que tengo interés en realizar es la siguiente. Si tomamos una ecuación y la representamos múltiples veces, y lo hacemos en una pantalla, en un ordenador, pues nos sale una figura. Estoy hablando de la representación de las ecuaciones fractales. Si nosotros cogemos el mundo, lo tomamos con las diversas fuerzas que hay, las fuerzas fuertes, y todo eso lo hacemos en un mismo proceso a todas las partículas, electrones y toda la materia que existe en el universo, podríamos decir, por ejemplo, que un ser humano, una persona, somos una ecuación fractal. Todo obedece pues, al proceso del sistema solar donde vivimos, y en definitiva, la pregunta sería, todo lo que existe en el universo, nosotros podríamos decir que un ser humano es una ecuación fractal.
Well, no, that's a very interesting question. And you see, I think the problem here is, you might say that at the most basic level, you have quarks, and they form protons and neutrons, and then they form nuclei, and then you form atoms, and you put the atoms together, and you form the molecules, and then you produce more and more complicated molecules. If we had the universe's calculator, we could understand it from that point of view. But there is no way, I think, that we will probably ever be able to formulate this point of view into any kind of mathematical formulation that will produce the whole thing. We're just not smart enough. And calculators and even the biggest computers are not powerful enough to do that. Because biology is so complex that you have to deal with these things at a biological level, where you basically have another scale at which you try to understand things, where quarks and electrons and protons and neutrons play virtually no role. And I think that's what we're faced with. You know, in a certain sense, it's the old business. At one point, we thought there was something called the life force, and all living things have the life force. But now we know there is no such thing as a life force. The only forces we know of are the forces of physics, and they make a very complicated set of molecules. But how they are put together, in fact, tomorrow you'll hear some lectures about how complicated things are. The idea that we could ever really understand it from a physics point of view, totally understand it, I think is way out of the question. You know, there are certain things that you can understand if you take a sub-part and you sort of say, well, you want to use thermodynamics to see what the rate of this or the rate of that or things of that nature, that's okay. But you'll never understand, for example, the idea that there could be even any equations of DNA and the way DNA is assembled and how it transmits information to make new proteins and so on and so forth. That's just too complicated. I would ask my biological friends to see if they either agree or disagree.
Bueno, ya como tenemos otra conferencia, vamos a cortar las preguntas porque nos podríamos llevar todo el tiempo que quisiéramos con el profesor Friedman. Darle las gracias y bienvenido y que ha sido un orgullo que